Hey guys, we're back. Here's 23. Here's some function f of x is 2x plus e to the x, and we have g of x. Inverse of f. And so if g is the inverse, right, that means that we can swap x and y. Right? And our goal, again, is to find, g prime of 1. G prime of 1, and that's, we know this point up here is on the curve. Okay, so let's think about this guy. So if I wanted to now take the derivative with respect to x, right, that's just going to be 1, right, the 1, and we'll write it out, d dx of x, and then d dx of 2y plus e to the y. So this guy's just 1, right? And then this thing over here, well, this is 2 dy dx, and this is e to the y dy dx. Well, when y is equal to 1, we can evaluate this thing. I'm sorry, y is not equal to 1. When y equals 0, we can evaluate this thing, right? Because this thing says 0 and 1, right? So this says f of 0 is 1, but since g is the inverse, right, g of 1 would be 0. G of 1 would be 0, right? So this is really the y here. So when we plug in 0 for y, right, we're going to get 1 equals dy dx times 2 plus e to the 0. E to the 0, right, of course, is 1, right? So we're going to get 1/3 equals dy dx. So that guy is 23. I seem to have misplaced my list of what you guys wanted to go over. Here it is. Okay, so the next thing, right, we said 25 is not yet. The next thing we said was 27. 27. That's talking about the height of some object given by this lovely equation. Yikes. Okay, and it says, what's the average height of the object from 0 to 2? Well, we know what the average height is, right? The average height is simply given by, from 0 to 2 is 1 over 2 minus 0 times the integral from 0 to 2 of this mess, right? This mess, that's what that average value is, right? Well, we can just take this, right? This is 1/2 times the integral, right, which is going to be 16t plus, oh boy, we're going to get a pi over 4 that comes out, right? So we're going to need a 7, and then we're going to need a 4 over pi to reverse that chain rule. And I think sine of pi t over 4 evaluated at 0 and 2. So you can work this out, right? This is it's going to be 1/2 of 32 plus, oh boy, 28 over pi sine of pi over 2, which is 1. So that's good. And then when we plug in 0 here, the second time they're both 0. So it's just this thing, which I think is 16 plus 14 over pi, which hopefully is an answer. Okay, that I think concludes our non-calculator multiple choice. The calculator multiple choice, there were a couple where we haven't learned how to do those yet. That's totally fine. Don't be afraid. And then some of them where you guys could know how to do them, but you might not know how to plug that into your calculator unless you took AB last year. And we'll go over that in good time over the rest of this year together. So 78 was the first one that you guys really wanted to look at. This one was a little tricky. So we had integral from 0 to 10 of f of x dx was 21. And we had integral from 0 to 10 of 1/2 g of x dx equals 8. And now, right now, I'm just going to take this and I'm going to make this look nicer. So if I pull that 1/2 out, if we pull the 1/2 out, right, we can get this. It's the same thing. And if I multiply by 2, right, I can have this. That looks a little bit nicer, right? And we're going to want to use that. So then we're given later on that this integral, so we have this as a given, we have this as a given, and then we're given that from 3 to 10, f of x minus g of x dx is 2. And it asks us to find this integral from 0 to 3, right? So it says, what is this guy from 0 to 3, f of x minus g of x dx? Well, we know what that is from 0 to 10, right? We know from my box things above, right, that from 0 to 10, f of x minus g of x dx has to be 5, right? Because we have the 21 and the 16, right? And therefore from 0 to 3, right, 0 to 3, this guy has got to be 3, right? Because they have to add together to give me 5, right? So I think 3 would be my actual answer. Okay, let's think about 80, because 80, I know we touched on it, but this is something that I'd like to delve into a little bit more. So we have the position of a particle traveling along a line. It's given by some function s. If s is increasing from 0 to 2 and decreasing for t is greater than 2, which of the following is the total distance the particle travels? Okay, which is the following which is of the following is the total distance the particle travels? Okay, so let's run through them. Let's run through them and see if we can make some sense. So we've got this guy. Total distance the particle travels. Okay, so we're concerned about distance the particle travels. Let's talk about A, and actually let's talk about B together, because they're similarly wrong. Okay, so we know we're decreasing from 2 to 5 and increasing from 0 to 2. And I don't really care about that, okay? Why are these both wrong? Well, they're both wrong, right? Because if we're looking about the distance the particle travels from 0 to 5, I do not care where the particle started, right? It's like I always say, if we're driving down a highway at 60 miles an hour for 2 hours, we know we went 120 miles. That has nothing to do whether we started in Pittsburgh or whether we started in Montana, right? It does not matter. We still drove 120 miles in those 2 hours. So these guys are wrong because they include this thing, okay? It does not matter where we start. Let's think about the next one. So we have these two integrals, right? And this is saying this guy is where we're decreasing, right? So s prime is negative, and here we're subtracting where it's positive, right? So that doesn't seem like that's going to give me a very positive answer, right? We know s prime is going to be negative in this interval, it's going to be positive in this other interval. So this guy going to be negative, and that is probably not going to be great, right? We probably didn't go a negative distance in that interval, right? Can't really go a negative distance. So let's talk about the last two, because one of them has to be right. So we have the absolute value of this guy. That's interesting. And then the other one, we have the integral of the absolute value. Okay. And so we want to think about this is if these guys sort of canceled each other out, right? So let's say my velocity graph looked like this, right? I was positive, here's 2, very not the scale, and here's 5, right? I was positive to the left over here, and I was negative to the right over here. And these areas sort of canceled each other out. Well, right? We may have gone somewhere, right? We may have gone somewhere, but simply taking the absolute value of everything, right, might not help me, right? Because we're talking about distance traveled, not displacement, distance traveled. So we certainly were going somewhere over here, and we were going somewhere over here. Even if we ended up back in the same place, we went somewhere both times, right? We were increasing somewhere, we were decreasing somewhere. So taking the absolute value of the whole thing, if those areas are equal, that's going to be bad, right? We might get 0 here. Whereas if I took the absolute value of just the function down here, right, I might end up with something that looked like this, and then that makes more sense, right? I want all of this area, and I want all of this area. So I think it's E. E sounds like a good answer to me. All right. 81 and 82 are examples of things that you would use your calculator on. okay? And I think you guys would all be very capable of plugging that in if you had your calculator available. Okay, I think 81 we could actually just do, right? Because 81, we're trying to take the integral of that guy. We're trying to take the integral of that guy. Well, let's do 81. We could do 81 without a calculator. Well, I mean, we need a calculator to do the arithmetic, but we don't actually need it to understand the calculus, right? There's some of them that you're going to actually have to evaluate an integral on your calculator. This is not one of them. Okay, so this guy, right, that's the rate at which our temperature is changing or something, right? And we want to find the temperature at 4 minutes. At 4 minutes, okay? And we're given that T of 0 is 200 or something. Okay, so we want to take the integral of this thing to find that temperature equation, right? And so the integral of r over t dt is going to equal that some temperature, right? And so that, of course, is going to be 6.89 over 0.053 times e to the negative 0.053, right? You can verify that this thing's derivative is that thing up there, right? Plus some c. And we need to calculate what c is. So if e is 0, right, now we would just use our calculator, right, to do a whole bunch of math. So I think if we solve this out where I say 200 equals this thing, I don't have my calculator on me right now. I just have my notes from previously. Right, I think we end up getting c is 70. C is 70, and then if we plug in 4, I think we end up getting we end up getting a 175 degrees. You guys can verify that, but this is just a calculator exercise with some messy numbers. Don't feel the need to talk about that too much. 82, similarly, you guys could do this. I would just punch that in and graph it, right? And we're trying to find where it's a relative maximum, right? So you guys could study that graph and really look at that. That's not going to translate too well to the iPad, so I'm not going to try. Let's talk about 83, because that one was a good one. More Riemann sums. Okay, and the key here, using this table, is sort of say, okay, anytime they ask us what's possible, right? We know this function's increasing all the time. They're really asking us, if we use a left-hand sum and a right-hand sum, where would we, what bounds would we establish? So if we look at a left-hand sum here, the left-hand Riemann sum is going to be 1/2, and then all the left-handed intervals, right? Because they all have width. The width is always a half. 0 plus 4 plus 10 plus 18 plus 28 plus 40. If you add those numbers up, you get 100, right? So our average would be, or not our average, our sum would be 100, so we'd have 50 as a left-hand sum. Our right-hand sum, similarly, would all be these numbers. But 54 on the end, right? This is actually going to be 77. Okay, so that is A and C. And we know, right, that this guy looks is increasing all the time, right? So if a function's increasing all the time, right, it could look like this, it could look like this, but either way, if I take a left-hand sum, right, if we take a left-hand sum, right, we're gonna end up with this scenario here, where we're sort of underestimating every place, right? We're underestimating our curve. And if we took a right-hand sum, right, we'd be overestimating our curve at every given point, right? And it would have to lie somewhere in between. And that's going to be true for both of these guys, right? We're gonna overestimate or underestimate our curves. And so given that it must be somewhere in between, right? I think the answer has to be B. And if you took the trapezoidal sum or something, you get something very close to 62. But we know it has to be between 50 and 77. That's sort of the main piece there. 85. 85. Let's look at that. So a particle moves along the x-axis, so the time t equals 0, or time t is greater than 0, sorry. Its position is given by this nonsense. That'll be so fun to deal with. What is the velocity of the particle at the first instant the particle is at the origin? Oh boy. So the first instant the particle's at the origin. Well, this is a cosine graph. Right? And so since it's a cosine graph, we want this. This thing is at the origin when root t is pi over 2, right? Because then I would have cosine of pi over 2, and then that thing is going to be 0, right? So we want root t to be pi over 2. Well, let's think about the velocity. So the velocity function, if this is the position function, right? Well, let's take this, right? We're gonna have to change all this. So it's gonna be negative sine root t times 1/2 with that root t on the bottom, right? Because we're gonna get this is really t to the 1/2. So we're gonna throw that 1/2 down there, and we're gonna get something that looks like this. Okay. And we want to know what the velocity is when root t is pi over 2, right? Because that's when this thing is at 0. So when root t is pi over 2, let's just sub. We don't actually have to solve this. I don't want to know what t is. I want to know what root t is, right? All I see is root t's in here. So negative sine root t is just pi over 2. And then 1 over 2, pi over 2 down here. Right? That's all. I'm just subbing in for root t, which we said was pi over 2. So this is an instance where, right, we can be safe and not actually evaluate this thing up here. There's no need to. Okay, so what is negative sine pi over 2? That's just -1, right? Negative sine pi over 2, yes, -1. And then this thing over here is 1 over pi. So I think my answer is -1 over pi. If you actually do that out on your calculator, I think it's C. I think, right? -0.318. That sounds like about right. A little less than a third. All right, so that's 85. 86 was a fun one. I enjoy 86 ones. I don't know why they're in the calculator section. So we have something that says f prime of x is greater than 0 everywhere, and f double prime of x is less than 0 everywhere. Okay, so what on earth does that tell us? That tells us for f prime to be greater than 0, this thing had better be increasing everywhere. And for f double prime to be less than 0, it's concave down, meaning it's increasing at a decreasing rate. So let's go one by one and cross stuff off. So it can't be A because that guy isn't increasing. It can't be B because that guy isn't increasing, right? It can't be C because that is increasing at a uniform rate. Right, C is increasing at a uniform rate, goes 4, 5, 6. It can't be D because D is increasing at an increasing rate, goes 4, 5, 7. So it must be E, where we are increasing at a decreasing rate. I don't really know why I wrote stuff down here. I'm not going to copy all those tables. So that was 86. 86 has to be E. Okay. 89, we legitimately need to use our calculator. We're not going to do that one right now. And 90 had, again, that differential equation that we're not going to look at. You guys did want to see 91. Someone wanted to see 91. Let's look at it. Maybe actually, I think a lot of you want to see 91. So, plus we get to talk about FU here. So, we're looking at this guy here from 0 to 8, FU du, F of u, I should really say, is 6. But, we've been doing this for a while. And so what is this expression? Yikes. Well, if you were presented with this expression, you'd want to use u substitution, right? So let's let u equal x squared minus 1. Then du dx, well, that, of course, is just 2x. And that tells me that du over 2x equals dx. Good. Okay, so now let's actually delve into this and start moving some stuff around. Oh, sorry, I want to do one more thing. If x is 1, right, if x is 1, then u would have to be 0, right, because u from this thing right here, x squared minus 1, 1 minus 1 is 0. And if x is 3, the upper limit over there, then u, of course, is 8. Well, that's nice because those are my limits off here over to the left. So let's rewrite this expression to the right in terms of u. So that would be u goes from 0 to 8. And then I'm going to have this x. I'm going to have f of u. And then dx, remember we said was du over 2x. Well, that thing is just 1/2 f of u du, which is really 1/2 from 0 to 8 f of u du, which we know from the given is 6, right? So this is 1/2 times 6, or 3. Okay, that's 91. Last guy. Whew. It's been a long night of doing math on the iPad. Okay, so 92, the function f is defined for all x between a and b. If f does not attain a maximum, which must be true? Oh boy. Okay, so we have f is not continuous. All these things are on AB, right? B. F is not bounded. Let's see. F does not attain a minimum. F has a vertical asymptote. And f prime of x does not have a solution. F prime of x equals 0 has no solution. Right, so it's never horizontal. Okay, so let's think about what this thing looks like. F does not attain a maximum. So there are two ways things cannot attain a maximum, right? Two key ways that we can't attain a maximum, right? The first one is we have some vertical asymptote and we approach infinity. The second one, right, is we approach something and we sort of have some hole on there, right? So we definitely have the solution where we could have a vertical asymptote, but we need to sort of see is that true? Well, if it had a vertical asymptote and we approached infinity, that would be a way we didn't have a maximum. Then both B and D would both have to be true, right? We'd be unbounded and we would have a vertical asymptote. Well, they can't both be true, right? So neither of them are the correct answer, right? So there must be some other way. So let's think about what this thing might look like. What if I had sort of a volcano, right? What if I had something that looked like this, right? Let's say I just, maybe I have some linear function here, right? And then I have some hole up here. And then let's, who cares? I have some dot down here, right? And then here maybe I curve down. Who cares, right? So I have something that looks like this, right? That's definitely a function that's defined for everywhere. Okay, this function certainly attains a minimum, so see, it's not C. This function could have, right? Who knows? Maybe we come back up again. This function could have this, right? This thing, right? Could have a solution, right? But the one thing we know, right? F cannot be continuous. F cannot be continuous, right? So this is my correct answer, right? And we know that if F were continuous, right, we would have to attain a maximum somewhere, right? We can't have a continuous function without a maximum. So I think that one is A. I hope these two videos were helpful. We'll talk about some other ones in the future.